Hey everybody, welcome to day 4 of, okay, I guess it's starting now. Hello everybody, welcome to day 4 of game theory. Uh, Yesterday we were talking about Nash equilibrium, um, and we discussed cases, or one case, in which there was no Nash equilibrium. So today we're going to continue on that topic and explain just what you do in that case. So I'll explain what a mixed strategy is later, but you'll find out that's pretty self-explanatory. Okay, we have a game table. This is the beginning exercise. What's the Nash equilibrium? You can probably guess what it is, but show me your work, I guess. So just to make sure that everybody understood last class and hasn't forgotten it. I'll give you until, let's say 7:15. That's might be much. Or until somebody gets it. Whoever gets it first is cool. So that's your incentive. Alrighty. Okay, so people seem to be a little bit confused. So let's look at each case. Let's do case analysis and examine this game. So let's start off with player A. So if player B were to go left, would player A go up or down? Exactly, down. So, and if player B were to go right, would player A go up or down? Exactly. And then we do the same thing with player B. If player A were to go up, would player B go left or right? Left, exactly. And if player A were to go down, would player B go right or left or right? Exactly, right. So here it is. Here's the best case analysis, and you will notice that there's no overlap. So that means that there's no Nash equilibrium. Does everybody understand why there isn't? And does everybody understand why they? You can also tell me why you think you made a mistake. Did I not explain it well? Is something wrong? I don't know. But does everybody understand? Okay, that's fine. My brain also sometimes is slow. So as you can see, because there's no Nash equilibrium, players are still going to have to play the game, right? They can't just opt out. So how are they going to manage to play this? So what should the players do? So both players should choose options with specific probability. If it's a repeated game, then they switch. If it only happens once, then they basically just flip a weighted coin because there's two options. So the probability should be calculated such that the expected outcome is maximized, right? They want to get the highest possible outcome, the highest possible payoff using probability, right? So we denote these probabilities. So the probability that player A goes up is P, and the probability that player A goes down is 1 minus P. Everybody understand why? Everybody know how probabilities work? I see one yep. but this is kind of a more than one yep question, because if somebody doesn't, then I definitely need to explain it. All right, I see one yep and one yes. So I'm going to assume that everybody knows how probability works. Okay, so similarly, player B, the probability that they go left is Q, and the probability that they go right is 1 minus Q. So now we're going to calculate hypothetical payoffs, right? So this means that player A's payoffs are going to be something if player B chooses left and something if player B chooses right. And we're going to base this hypothetical value on the probabilities that player A has. So let's return to the game table. So if player A goes up with probability P, they get 5 points. And if player A goes down with probability 1 minus P, they get 9 points. So what is the expected value of player A if player B goes left? Okay, so not an integer, but I guess the expression. So yes, it is at least 5, but what is the expression to write the expected value of player A given player B going left? Q times 1 minus P or QP. That is, remember the payoffs are 5 if player A goes up and 9 if player A goes down, when we assume that player B is necessarily going to go left. So you want to incorporate that into your answer. Okay, so people seem to be a little bit confused, so I'll go through it step by step. So player A is going to go up P out of P percent times, right? So with P probability, they are going to get 5 points. So the first part of it is 5 times P. With 1 minus P probability, A is going to go down. So in that case, they'll get 9 points. So that's 1 minus P times 9, right? So if player B were to go left, player A would get 5 times P, and that's when they go up, and 9 times 1 minus P, because that's when they go down. And P is the chance that they go up, 5 is the payoff when they go up and B is left, 9 is the payoff when A goes down and B chooses left, and 1 is the probability, 1 minus P is the probability that A goes down. So does everybody understand where that, not equation, but representation comes from? If you want me to go through it again, just say so. That's also fine. I think this is kind of the turning point. This is probably the hardest class, the hardest lesson. So if you need help, that's perfectly expected. I needed a bit of help myself when I went through this class at this point. Is everybody okay with it? If nobody's going to say anything, then I think in this case I'm going to default to explaining it again. But so just there's nothing wrong with being, having a question. Once again, I had tons of questions in this class. So, all right, that's 1. If I don't get 2, then I'll go over it again, because that's an I think I understand, so I want to go over it. So if nobody else says anything, I will. Okay, I get 1 understand, 1 I think I understand. But there are plenty of other examples, so I can continue to go through this. Okay. So I'm going to move on, but I'm going to explain the next one just as in depth. Okay, so now we're going to look at the case that player B chooses right. So with probability P, player A is going to choose up. In that case, player A is going to get 8 payoff. So in that case, the expected value is 8 times P. If player A goes down, then they will get 2 points. And they're going that with a probability of 1 minus P. So then they'll do 2 times 1 minus P. So the total expected value is 8P plus 2 times 1 minus P. Does that make sense? Okay, I have 1 yes. I need a second yes in this case. I'm going to be slightly more taking my time on this one because I think I've been going through lessons too quickly. Alrighty, great. I see 3 yeses. I see a lot of yeses. Wonderful. Okay, now we're going to include player B's probabilities, right? Player B, we don't actually know what they're going to choose necessarily. They have their own probabilities. So the probability that player B goes left is Q, and the probability that player B goes right is 1 minus Q. You can remember this from the previous slides. Give me a second. Right, left is Q, right is 1 minus Q. Can you turn on the laser pointer thing? That might be helpful. There you are. So left is Q, right is 1 minus Q. So because we know the expected payoff if player B chooses left, we can multiply that with the probability that player B chooses left to get that expected value, which is 5P plus 9 times 1 minus P, all times Q, and then plus 8P plus 2 times 1 minus P, the expected value of player A, given that player B chooses right. And then that times the chance that player B chooses right is 1 minus Q. That is player A's net payoff, right? Given all the probabilities and given all the payoffs, this is what player A is going to get. Now we can simplify this to 2 plus 7Q plus 6 minus 10Q times P. But remember, player A only has control over option P. So given that, what do you think? Actually, I'm not going to ask what do you think. That's kind of a bad question. Okay. Okay, so let's go back to our equation. So it's not an equation, that's wrong. So we have 2 plus 7Q plus 6 minus 10Q times P. And notice how the coefficients on P is 6 minus 10Q. Also recall that player A can only modify P. So given what they know Q is going to be, we can make some deductions. So if Q is going to be greater than 0.6, then the value becomes negative, and P will become 0. Player A will always choose down. This is because when he is losing payoff on that second half, he's going to shut it down completely, right? So does everybody understand why, if Q is over 0.6, then player A is always going to choose down? Okay, maybe, yes, but let me try to explain it better because I don't think I explained it very well. Okay, so this equation over here, whenever I click back onto the PowerPoints, it advances a slide. Okay, in our equation, this is the equation for player A, right? Player A can only manipulate P. So whenever this part starts taking away from his payoff, from their payoff, player A is simply never going to choose it, right? They understand I am losing if I ever choose that because of how probabilities would work in this case. So I am simply never going to choose it. And instead, all of my payoff will come from this. So does that hopefully make it clear? If you have a specific question, that would be great because then I can address specific questions. Yeah, maybe I should have put the table, but because this is kind of a block of text, it's kind of hard to do. So here's the table again. I wonder if I can somehow put it. I'm gonna see if I can kind of put it in chat. That'd probably be hard. Okay. All right, so you don't understand where the 0.6 came from. That's good. Okay, that's something very concrete and something I can explain. Okay, so this is the nice long equation that is clear where everything comes from. When you simplify it to something where you split up the numbers where p is a constant and where p is not a constant, you get this equation. So when q is 0.6, 6 times 10 times 0.6 is 0, right? But if q increases, if q is, say, 0.7, then it would be 6 times 10 times 0.7 times whatever p is. And because 0.7 times 10 is 7, 6 minus 7 is -1, and then times p is negative p. So player A is actively losing points because they are choosing to go up. So does that make sense where the 0.6 comes from now? All right, let's go back to this slide. Okay. Similarly, when q is less than 0.6, that means that this value is going to become positive. So player P will always choose, P will become 1, that's at 100%, and player A will always choose up. This is by the same logic as always choosing down. They know that if Q is less than 0.6, then the value given by this part is going to be positive, so choosing P will always get them more points. Does that make sense? Wonderful. Okay. Does anybody else want to say that makes sense? Or say that it does not make sense? That's actually even better. Because if it does not make sense, then it will not make sense in the future. So now is probably the best time. Or I don't know. Yeah. So anybody want to say how they're feeling about this? I guess is the way to say it. Okay, no one's saying anything, so I'm going to, I think now it's okay to assume that people are understanding, but that is an assumption that you should break if you are not understanding, please. Okay, so, but this is only when q is greater than or less than 0.6. But when q is 0.6, player A is going to get the same expected payoff no matter what they choose, right? 0.6 times 10 is 6. 6 minus 6 is 0, 0p. Thus, no matter what player A does, it's not going to matter, right? So player A will simply just, whatever their options don't matter. Their expected value is the same. So that's probably the easiest one to understand. So do people understand that part when Q is equal to 0.6? Anybody can say yes, anybody can say no. Please, I just need feedback. I need to know when I can move on. How do you apply this to the table? Okay, that's a pretty fair question. Basically, all it means is that when if player A were to hypothetically know how player B were to act, then they would know how often they should choose up if the game were to repeat, and how often they should go down if the game were to repeat. So if player B were to choose, if Q was greater than 0.6, player A would, I'm forgetting, if Q were greater than 0.6, player A would always choose down, right? But if player B's probability, if Q was less than 0.6, player A would always choose up. And if player B's Q were exactly 0.6, player A would probably just flip a coin. What they did wouldn't matter. The expected payoff would always be the same. So that's how they would do it. However, these are only the rules for player A. We can use the same method for finding out player B, and because both players are logical, they can both do this computation, and from that they will reach a conclusion, and we'll discuss what that conclusion is later. So does that make sense? Basically, okay, Q is the probability that player B will choose left, and 1 minus Q is the probability that player B will go right. Did I explain that? Does that make sense? P is the probability of player A going up. 1 minus P is the chance that player A goes down. Q was the probability player B goes left. 1 minus Q is the probability that player B goes right. Everything okay then? So the probability has to be greater than 0.6. So if the probability is greater than 0.6, then P will be 0. So the payoff that player A will get is like 2 plus 7Q. If Q is less than 0.6, then P is 1. So for given any Q, you can calculate what the expected value for player A is. So if Q is greater than 0.6, player A wants Q to actually be 1, right? Because that will maximize the part that he actually cares about. Because when Q is greater than 0.6, this part, P becomes 0, and then this part is void. This needs to be as large as possible for player A to get the most outcome. So he would prefer that if Q were to be greater than 0.6, that Q is 1. The same goes, the reverse is the case for Q is less than 0.6. He wants the parts that they actually have impact over, because player A can control what P is, and he controls it to be 1. So he wants that to be the greatest, because the less that this is, the larger this 6 minus 10Q is. So player A hopes that if Q is going to be less than 0.6, that Q is 0, because then it's 6P, right? Actually, is that true? That's not true exactly, actually. You, disregard what I said. I did the math wrong. Ugh, that's not good. That's not good. Okay. The probability to, I'm trying to understand what you mean by that. Could you clarify a little bit? So the 0.6 simply reflects what player A will do given some specific probability that player B is going to choose going left or right. So player A is going to never choose. So a reminder that players do not want more payoff than the other player. They simply want to gain more payoff for themselves. So just players don't care about the other player's payoffs. They only care about their own payoffs. So this is the, let's go back to the long function. Let's look at both of these, right? So when we are given what P is, and when we are given what Q is, we can calculate what player A's expected outcome is, right? So we plug in, P, let's say it's 3/4, and Q is, 5/7 or something. I don't care. And then you plug it in, and that is player A's expected payoff in a given round. And if you repeat this game a bunch of times, your expected payoff for player A over the expected average payoff for player A is this. So does that make sense? Am I making sense? So is your question gone? I guess is another question. Has any if Q equals left, what do you mean by if Q equals left? Q is simply the probability. Okay, wait. Okay, I understand. Okay, if Q is the probability for left, then 0.6 would mean most likely to choose left. So why wouldn't A choose down? Because that is not necessarily the case. Player B, just because it's more likely, doesn't mean that player A should always go down, because it's about a 50-50 split, right? So player A should vary between going down and up. Does that make sense? And then the second question is, they still want the highest payoff, which creates a clash. Yeah, basically, even though they aren't specifically competing to get the higher payoff, they're still competing to get the highest payoff. So yeah, that's where the, I guess, conflict arises from. So does everybody understand everything? Any questions are good, because it is very good. I appreciate questions because it shows me that you're paying attention. Okay. So now we have this set of rules. If the chance that player B goes left is greater than 0.6, the probability that player A will go to down is 100%. And if Q is less than 0.6, so chance that player B goes left is less than 0.6, then player A is always going to go up. And if Q is exactly 0.6, player A is always going to get the exact same expected payoff. So they basically can choose at random. So these define player A's best response rules. Technically, we haven't solved it yet, however. So now we have to do the same thing for player B. So player B's response rules. So let's look at the chart again. This is why I wanted to make sure that everybody understood, because I'm going to make you guys do player B's response rules. Just so create the response rules and create the formula for for player B's expected payoff. Maybe we'll just do it, show your work, do one step at a time, and thus that way I can make sure you're not making any mistakes partway through. So remember, we assume if player A goes up, what are player B's expected payoffs? If player A goes down, what are player B's expected payoffs? And then, you know, given the probabilities of up and down, what's player B's net expected payoff? And then I'll take it from there because the simplification is always annoying and it's never fun. So this one's going to be long. I'm probably actually going to give you until somebody gets it, or until, I don't know. I'm going to give you guys a while. That's all I'm going to say. I don't know. This is definitely going to take some time. So does everybody understand what we're doing? I'm trying to make you guys be more engaged. That's something I realized that I probably should be doing. Alrighty. Wonderful. Don't be afraid to ask questions still. If you want to ask a question and not give away things, you can privately chat me if you really want to. You can also not do that. I don't care. So I don't know if I should be saying best of luck, but hopefully I explained it well enough such that everything is clear. I think that's a good way to phrase it. Alrighty. So yeah, go ahead. Just to make sure everybody understands, you don't have to do the response rules, just give expected value. I'll do response rules myself. So if you remember that long equation with q's and p's and 1 minus p's and 1 minus q's that we did for player A, we're just doing the exact same thing for player B. So some people want to see the previous slide, so with reference. So I'll do that. Here you go. But then you guys can't see the actual table. That's a problem. I guess jot notes down for what it looks like. I'll intermittently go between this slide and the previous slide. So yeah, I'll stay on this slide for a little bit. Oh wait. All right, somebody wants to see the table. Here you go. Here's the table. Okay, we aren't stopping, don't worry. But I think the stopping time that we need is 7:50. Or actually, perhaps we should stop now. Um, let's take it in the middle. I'll give you until 7:48. So 2-ish minutes. Don't worry if you don't get it done by then. This is really just, once you understand it, it's basically just manual labor. So don't worry about it. Somebody wants to see the table, so give me a second. You guys can see the table, right? All right, give me a moment. I'll be right back. All righty. So people seem to be getting it right, which is good. So let's look at the table, right? So if player A were to choose up, player B would get 5 payoff if they went left. So they go left with probability Q, so that's 5Q. And if they were to go right, they would get 8 payoff, and they go right with probability 1 minus Q. So that's 8 times 1 minus Q. Similarly, if player A were to go down, player B would choose left with probability Q, netting payoff 9, so 9Q. And player B would go right, 1 minus Q probability. I've been reading the wrong payoffs. Oops. Excuse me. Let me redo that. So if player A goes up, player B goes left, so then it's 5 times Q. If player A goes up again and player B goes right with 1 minus Q, there's a payoff of 2, not 8. I read the wrong one. So then it's 2 times 1 minus Q. If player A goes down, player B goes left with Q probability and gets a payoff of 1, so just 1Q. And then again, player B, if player A is going down, if they go right with 1 minus Q probability, they'll get a payoff of 8. So it's 8 times 1 minus Q. So then the payoffs are 5Q plus 2 times 1 minus Q if player A chooses up, 1Q plus 8 times 1 minus Q if player A goes down, and then you multiply that with A's probabilities. So then it's 5Q plus 2 times 1 minus Q times P, all, you can see it, I don't have to say in brackets, plus 1Q plus 8 times 1 minus Q, all times 1 minus P, which can be simplified to that expression. I am pointing to it on my laptop, but you cannot see because that's not how pointing works. So that's how it is. Does everybody understand? I got several correct answers, one of which was not in the form I expected, but was very much correct, and I accidentally said it was wrong, which is not good. So sorry about that. But does everybody understand? I see one yep. Let's get another one. And I see a yes. Alrighty, wonderful. So we are going to use the same method for that we use for person A for person B. So we look at the coefficient of Q right here. Can you see my cursor? I don't care. I mean, I do care, but you can see it. So the coefficient of Q is 10p minus 7, right? So because Q is the only thing player B could change, we are only going to analyze that 10p minus 7. So and p is less than 0.7, the coefficient becomes negative. So Q should be 0. So player B is always going to choose right because they do not want to be losing expected payoff because they are, sometimes going right. Similarly, when p is greater than 0.7, the coefficient becomes positive and player B is always going to choose left. P will be 0. I mean, Q will be 0, pardon. And then when p is equal to 0.7, player B will get the same expected payoff no matter what they choose. So does everybody understand where these came from? Come on, some yeses, some nos. I just need confirmation that people either understand or don't. Either one is fine. Okay, I see plenty of yeses. So now we have the best response rules for both players A and B. So let's go back to player A's. So based on this, we know that if Q is greater than 0.6, A will necessarily go hard one way. If Q is less than 0.6, player A will go hard one way. And if Q is exactly 0.6, then player A is going to, adapt. So now we go to player B. If player A's probability is less than 0.7, Q is going to skew hard. If Q is greater than 0.7, Q is again going to skew hard, but in the other way. And when P is 0.7, player B is going to choose something. So given that, what do you think both players should do? What probability should both players use? What should P be and what should Q be? Okay, we have one possibility. Anybody else have any possibilities? Is that a no as in the person above you is incorrect, or a no as in nobody else has any other ideas? Okay, that's a no ideas. That's what I was hoping, because that answer is correct. P should be 0.7 and Q should be 0.6. Basically, what we have calculated is called the mixed Nash equilibrium. It is similar to a Nash equilibrium, such, in a way that you both players have to choose such that if they skew one way, they'll get, if they skew from the Nash, they'll lose value. And mixed Nash is basically the same, except if they move, they get hits in the expected value and not in the value technically. So this is a bit more evident when you look at the graph. So on the left, we have the P versus Q graph for player A. And on the right, we have the Q versus P graph for player B. So we can see that, so let's start off with the leftmost graph for player A. So when player B has a probability, has Q from 0 to 0.6, P is equal to 1. And then from 0.6 to 1 for Q, P jumps from 1 to 0. However, in between, at exactly Q equals 0.6, P forms a vertical line. Basically, that means that P can take any value and the expected value will not change. Similarly, for player B, we have the Q versus P graph. So when P is from 0 to 0.7, Q is 0. When P is from 0.7 to 1, Q jumps up to 1. And when P is exactly 0.7, Q can be anywhere. And to make sure that everything lines up, you simply reflect the first graph along the line P equals Q. That's just making sure that the P and Q axes meet up, and you get this graph. And you can see that the intersection occurs when Q is equal to 0.6 and P is equal to 0.7. So yeah, that's how it is. I think this is a very interesting solution. I personally prefer doing it the whole way out, but if you're more comfortable graphing it, that might be better. Sometimes it gets long and complicated though, but when you're doing mixed Nash, I would advise using this full method, but you can also graph. So does this graph make things clear? And is everything clear, including the graph and including all the ideas I've presented, I guess? Okay, that's one yes, that's good. Any other questions? Any non-questions? Anything at all. I will answer basically any question. Is anybody at all confused with anything? Alrighty, I'll give you 35 more seconds. And all right, 5 seconds. You have 5 seconds before you can ask a question, and then I'm gonzo. 5 seconds are up. Okay, well, that's the class. I hope everybody learned something today. Today was an especially important class, and I will see everybody Tuesday. You can always, if you have any questions that you didn't want to ask now, or maybe you just didn't realize you need to ask, you can always reach out to me on the Ed page. So do that. All right, bye-bye. Gonna end now.